Welcome to day 9 of 50 days of tutelage. Today we're going to be dealing with chemical bonding. This is the first part. There's going to be a second part as well. And if you have been following this class very, very well, you know that we have been discussing a whole lot of things, especially in chemistry. We've done atomic structure, we've done periodic table and trend. So you can always check all of those videos back. Anyways, get your notes and your pen. We're about to start this whole thing. Now, what is bonding? Bonding basically is the force that holds it holds either atoms or ions in either a compound or a molecule. I'm going to be explaining the concept of molecule and compound very soon briefly. Now, what is molecule and what is a compound? For molecule, what happens is that there's always a sharing of electron involved, and also molecule can have just one person, just one atom rather, the same atom sharing with itself. For instance, you can have a molecule of oxygen, so this bond is between oxygen and oxygen. You can have a molecule of hydrogen, it is between hydrogen and hydrogen. But for compounds to be formed, there has to be at least two different atoms in the process. For instance, this is between oxygen and hydrogen. So this is a compound, but this can also pass as a molecule because there's a form of sharing that is going on in this place as well. So that's the basic difference between compounds and molecules. I believe we're going to be talking more about that in our subsequent teaching. So bonding is basically the force that tends to hold these things together. For instance, if you have a compound like NaCl, what is holding them together? That is what we call the chemical bond. Now, this bonding are they are actually in two major ways. We have what we call the ionic bond, or what we also call the electrovalent bond, and then the second one we have what we call the covalent bond. Covalent bond. I'm not going to be discussing about covalent bond in this particular class. I'm going to be discussing about it in the chemical bonding part 2. So the general statement I said that not all compounds are molecules. So something might be a compound and it will not be molecule. So you'll find out why some things are compounds and they are not regarded to as molecules. Like you cannot say a molecule of NaCl now. You cannot say that. So you're about to find out in this particular class. So the first thing I'm going to let us understand is that why do these guys want to bond? For atoms, for them to want to bond, the reason is because they want to attain what we call stability based on the octet structure. So based on the octet structure, although there's also what we call the duplet structure as well. So what is octet structure? Octet structure is simply having like 8 electrons in your outermost shell, and duplet is when you have 2 electrons in your outermost shell, making you behave like any of those inert gases or group 18 elements. I'm talking about helium, I'm talking about argon, and so on and so forth like that. Now, the octet rule and the duplet rule is simply the reason why there is chemical bonding in process, because these guys want to reach what we call stability. Now, this can be done in so many ways. This can be done by transferring of electrons, receiving of electrons, or even sharing of electrons. So this is how atoms tend to interact with each other. Okay, this is atom K, this is atom Y. So they communicate with each other. What's up with you? Are you complete? No, I'm incomplete. Would you like to be complete? Like all of those things. And they try to like interact with electrons between each other or even among each other, depending on how many of them are together. So in the case of this concept I want to discuss in the part 1 of this class, we're going to be talking about we're going to be talking about giving out and receiving of electrons. So I'm not going to be explaining anything about sharing in this place. Now, also another important thing is that for most part of this class, I will be excluding most information about transition elements, the transition metals. So I'm going to be explaining strictly based on the group 1, group 2 elements, and from after transition elements upward, that is from group 13 to group 18. I'm going to be discussing mainly on that. So whatever I'm going to be giving as an information, until I say, oh, I'm talking about transition metals, just assume that I'm only talking about the representative element from group 1, group 2, and jumping to group 13 to group 18 like that. Now, what really happens is that if you look at from group 1 to group 2. Like I told you, the number of electrons in their outermost shell is 2. This one is 1. For group 1, the number of electrons in the outermost shell is always 1, and that of group 2 is always 2. And for group 13 to 18, what you notice is that number of electrons in the outermost shell is ranges from 3, 4, up to 8 like that. And these 8 are the inert gases. These ones, they already satisfy the octet rule or the duplex rule as the case may be. So their number of electrons is already complete at the outermost shell. Now, like I said, I'm not involving transition element yet. So I'll talk about them later. So for these guys now, they want to interact by either deciding that I want to receive an electron or I want to give out an electron. So receiving or giving out an electron, who can give out and who can actually receive electron? Here's what happened. You notice that there's a borderline between these people is such that if you have somebody that is in group 1, there are two things that they can do. They can decide to either give out or they can decide to what? Receive if they are in group 1. But if they're going to give out, how many electrons will they give out? Take note, the valence electrons are being used for all these transactions. So we don't use any inner electron. I'm going to repeat again. When I say we don't use any inner electron, I'm talking about the representative element only. I'm not talking about the transition element. So I'm not going to repeat this again. Just take note of it as we continue the class. So giving out, they can give out 1 electron in their outermost shell. Because if they give out 1, and the reason why they would have 1 electron in their outermost shell is that their previous shell is already complete, is already completely filled. So therefore, once they give out 1, then the previous shell will stand as a stable structure, will stand as a more stable guy. So therefore, they can give out 1 to become stable. But another option is also for them to receive something that will make their outermost shell 8. They have 1 already, so how many can they receive? That is 7. So the question is that the amount that they have to give is way lesser than the amount that they have to receive. So therefore, the favorable thing to do there will always be to give out, because it's like two people are trying to decide who will give and who will receive. But if I'm giving, I'm going to be giving way less than you will be giving if you have to give out. So therefore, somebody has to decide to give out, and the person that is giving out way less will be the person that would be giving out. So therefore, the person that would have given out way more will now be the receiver. So there's a way I usually tag them. There are some things. There are people we call perfect donor, and then we have people we call perfect receiver. People in this case, I mean atoms. So there are atoms that are perfect giver, and there are atoms that are perfect receiver. So any atom that their number of valence electrons is from 1 to 3. These guys, they will be perfectly givers. Because if you do for group 3 elements now, so you do the same process. To give, they have 3 to give. But to receive, to become 8, they have 5 to receive. So that means that giving is still the lesser one there. So therefore, they rather give. Now, for when we get to group 4, they are borderline, because for you to become 8, they can give out 4, and they can also receive 4. So these guys, that's why the metalloid guys, they don't really participate in this giving out and receiving like that. So group 4 is the borderline. So the moment you leave group 4, when I mean group 4 now, I'm talking about group 14. So I'm not talking about the transition element. So just permit me to use group 4 for the purpose of this video, using the number of valence electrons that they have to identify them. So group 4, based on the first 20 elements. So the group 4 guy at the borderline. So when I go to group 5, I go to group 6, and I go to group 7. So you notice that group 5 have 5 to give out. They can give out 5. But how much can they receive? They can receive 3. So therefore, the lesser part will always be the favorable part. The lesser part will already be. So when you want to decide whether something is a perfect donor or a perfect receiver, determine how much they stand to lose and determine how much they stand to gain. Whichever one is the lesser value there is the one that they will favor. So they will always favor the one with the lesser side. So finally, let's do for group 7. So group 7, they have 7 in their outermost shell. So how much can they give out? They can give out 7. And how much can they receive? They can receive one. So which one is the lesser part? It is one that is the lesser. Sorry, it is the receiving that is the lesser part. So therefore, group 7 guys will be perfect receivers of electron. So now that we have determined who are perfect donors and who are perfect receivers, then let's go to what we call formation of ions. Formation of ions. So you remember earlier I had defined that bonding or bond is simply the force that holds atoms or ions together in molecules and compounds. So what we've talked about atoms in all our previous lectures, so you know all of that already. Now, what are ions? Basically, ions are formed whenever there is a loss or gaining of electron. So if any atom had lost, let's say, an electron, or they have gained an electron, what they become then is that they become an ion. And then we have the positively charged ion, which are known as the cations, and the negatively charged ions, which are known as the anions. So how do they form? So let's pick any random guy from, let's say, group. Let's say we want to pick somebody from group 2 now. From group 2, so I'm going to pick calcium. Calcium is in group 2. So calcium is in group 2. The atomic number of calcium is 20. So if you write the electronic configuration, you're going to have 1s2, 2s2. You're going to have 2p6. So after 2p6, we have 3s. So we have 3s2. Then after 3s2, you're going to have 3p. You're going to have 3p6, and you're going to have 4s2. So let's see if that's complete. 2 plus 2 is 4. 4 plus 6 is 10. 10 plus 2, 12. 12 plus 6 is 18. 18 plus 2 is 20. So like I already explained to you in previous class, you know that the valence electron here is going to be at the highest energy level. For this one, it's going to be at the highest energy level. So therefore, it has 2 electrons in its outermost shell. So if it has 2 electrons in its outermost shell, that means that it is going to lose 2. Because if it wants to gain to become 8, it has to gain 6. So therefore, it can lose 2. So whenever it loses these 2, then the electronic configuration does not include this 4s part again. It now includes only this to the 3p6. Now, you would think that this has become the guy before this, and which is what? Argon. I think, yeah, this is for argon. Argon is number 18. So, but that is not it. Anyways, that's another way we also write electronic configuration. For calcium, I can just say argon, then I will just write 4s2, showing the immediately completed structure or the completed atom before it, which is going to be an inert gas. So that's just a digression. Let's go back to what we're talking about. So when Ca becomes this, it is not as if it's becoming argon. It becomes what we call Ca2 plus. Why is it Ca2 plus? Because if it has if it already lost the 2 electrons that are in the outermost shell, then it will become deficient, electron deficient. And when I explain to you that neutral atoms, what makes them neutral is because the number of proton is the same as number of electrons. So if you have 4 here, you have 4 here. But in this case now, in the case of calcium, you have 20 proton, you have also 20 electrons. So the moment 2 electrons are lost here, so you have 20 protons and you have what? 18 electrons. So whoever has the higher number will be the dominating power. So therefore, this guy is the dominating power. So you have a positively charged ion. So this calcium now has become calcium ion, and it is in the +2 state. Why? Because it lost 2 electrons. So when they lose electron, they become positively charged. But the converse is the opposite is what happened in the case of negatively charged ions, which are anions. When they gain electron, they become negatively charged because now they will have more electrons than protons in their outermost shell. So this is what happened during bonding. So how do we now determine the perfect fit for these guys? The first case, the first level that we take note is that if somebody can lose 2, like this calcium now, can lose 2 electrons, then if we need to lose 2 electrons to somebody who can actually gain 2 electrons, that would be the perfect match. So that is why you see that. So at the first instance, group 1 element will find group 7 element as a perfect match because I can give out 1, you can receive 1. So that's just a perfect thing. Group 2 element, we find group 6 element as a perfect match. Group 3 element, we find group 5 element as a perfect match. So the first phase of bonding is going to be this. Don't forget we're talking about ionic bonds here, where there will be a donor and there will be a receiver. So if you can lose one, then you need somebody who only needs one. If you can lose two, you need somebody who only needs two, and so on like that. So looking at this calcium now, let's pick a random guy in group 6. That is going to be oxygen. So oxygen, the electronic configuration of oxygen is 1s2, 2s2, and that will be 2p4. 2p4, I think that's it. Oxygen is number 8, so 2 plus 2, that's 4. And here 4 plus 4 is 8, so that's complete now. So this is group 6. Now I told you already that whenever you are in group in any of the apart from transition metals, whenever you are with any of the representative elements, all you have to do is that look at the highest energy level. So the highest energy level here is level 2. So what's the total number of electrons that we have here? 2 plus 4. So the number of valence electron is what? Is going to be 6 here. By the way, oxygen belongs to group 16. If you have not watched the previous video, some of the things I'm going to be saying here might be confusing, but I'd already explained a lot there. So if I'm maybe jostling between group 6 and group 16, I'm calling group 16 group 6. It's just for better communication. I've already clarified that in a previous video. So please kindly check the video out. Now, so 2 plus 4 is 6. That's the group of this guy. So therefore, Ca is ready. So Ca is ready to give out 2 electrons. And oxygen has 6 electrons surrounding it. So Ca is ready to give it out. So therefore, when this is done, Ca we now have total of 18 electrons around it, and oxygen we now have total of 8 electrons around it. So what you notice is that this Ca is stable. This oxygen is also what? Stable, because this is like element number 8, that is neon. So this is like neon, an inert gas, which is stable. And this is like argon, another inert gas, which is what? Which is stable. So therefore, through this transaction, they have been able to give each other something. So one has received, sorry, one has been able to give out, and the other has been able to receive. So therefore, you have a compound formed in this place, and this compound is going to be CaO. When bonds are formed like this, so that there is a losing of electron and there is a gaining of electron, then what you have there is what we call a chemical compound. And the kind of bond that exists there is an ionic bond, or also known as electrovalent bond. So the kind of bond that we have there is called what? Ionic bond. So generally we perceive that metals, they lose electron. So between metals and non-metals, generally you most likely will have ionic bond, but it goes a lot deeper than that. Even sometimes you can have metals form some non-ionic bond with non-metals. So we're going to be talking about that one later in part 2 of this lecture. So CaO, that is calcium oxide, this is an example of an ionic compound. Let's take another example. This time around, I'll be picking somebody from group 1 and group 7. So let's say we pick sodium. Atomic number of sodium should be 11. And then let's say we pick chlorine. Atomic number of chlorine should be 17. So let's write the electronic configuration. We have 1s2, 2s2, followed by 2p6, and then we have 3s1. For this other one, we have 1s2, 2s2, 2p6, 3s2, and this should be 3p5. Let's see if that's complete. This is 10, 17, this is 10, 11. Okay, so now they are complete. So from what we see here, we notice that the number of electrons that sodium has in its outermost shell, the highest energy level is energy level 3, and the number of electrons it has is 1 electron in its outermost shell. So 1. And for this, highest energy level is level 3. The total number of electrons is 7. So therefore, this can lose 1 or gain 7. this can lose 1 or gain 7. And this can lose 7 or gain 1. I told you that whichever side is the smallest one will be the favorable side. So for this, it can lose 1 or gain 7. So what would you rather do? It's going to lose 1 to this chlorine here, and therefore this one is going to be added. One more electron is going to be added to this one. So this particular part is gone. Then you have this left for the sodium. So therefore, since it would have, lose 1 electron, so that will be Na plus, and then this will become Cl minus. And the two of them can bond together and form a compound known as sodium chloride. Sodium chloride. So this is also another ionic compound. So I've been able to do group 2 and group 6, and I've been able to do group 1 and group 7. So the question is that, is it not possible for somebody from group 1 to bond with somebody from group 6? Because I've already told you that group 1 to group 3, they are perfect donors, and group 5, group 6, and group 7, they are perfect receivers. So does it mean that group 1 we always have to pair with group 7, group 2 we always have to pair with group 6, or group 3 we always have to pair with group 5? No. Any of these perfect donor can actually pair with a perfect receiver. It can pair with a perfect receiver. For example, you can have what we call aluminium chloride. You can have what we call aluminium chloride. And so let's see what that would look like. Aluminium, that is in group 13. In this, for the case of this video, we'll say it is in group 3. So aluminium is in group 3. Let's see what is the atomic number of aluminium. I think that should be 13. That should be 13. That should be 13. Yeah, that should be 13. That should be 13. So 13, atomic number of aluminum is 13. Let's pair it with oxygen. So oxygen is, I think I did oxygen earlier. Yeah, oxygen, atomic number of oxygen is 8. So let's write their electronic configuration. So we have 1s2, 2s2, 2p6, and this will be 3s2 and 3p1. So this is 1s2, 2s2, and this is 2p4. So let's see, 2 plus 2, 4, 6, that's 10. 10 plus 3, that's 13. So the number of electrons that this has in its outermost shell is going to be 3, because the highest energy level is level 3. For this, the number of electrons that it has in its outermost shell is 6, because highest energy level is level 2. So this is going to be a donor, because it has 3 electrons in its outermost shell. So it's either it lose 2 electrons, or it what, or it my intention was not actually to use oxygen. My intention was to use chlorine, but it's okay. So we have 3 electrons. It can lose 3 electrons, and it can also gain 5 electrons. So what would be the best thing? The best thing for it will be to lose the 3 electrons. And for oxygen, we have 6 in the outermost shell. So it needs 2 electrons to complete its octet structure. So it can either maybe lose the 6 or gain 2 more. So what would be the best one? Is to gain 2 more. Is to gain 2 more. So the valency of an atom is also another concept we need to know about. The valency of an atom is defined as the number of electrons that is needed to be received or to lose to attain the octet structure. So meaning that these guys, they need a number of electrons, whether they have to gain it or they have to lose it, they need it to attain their octet structure. So this number of electrons that they need to lose or to gain is their valency. So for this time now, this guy now is 3. For aluminum is 3, and for oxygen it is 2. So what happened is that these two would like to bond in that manner. And so the way they work is that they are going to we do something that we can call like something like cross multiplying. So this goes to this and this goes to this. So for this to happen, you have Al. Now the number that you have here is what? Is 2. And the number that you have here is 3. So oxygen is going to take 3. So the implication of this is that you have a formation of Al3 plus and O2 minus. Al3 plus and O2 minus. This is signifying that aluminium we lose how many electrons? We lose 3 electrons and become Al3 plus. And this shows that oxygen will gain 2 electrons to become O2 minus. But the case is that in this place we have 2 atoms of aluminium, so therefore the balance thing will be to put a 2 behind this. So it is 2 atoms of aluminium, and then how many atoms of oxygen do we have here? 3. So 3 atoms of oxygen. So let's go over that again. If aluminium is going to lose electron, it can lose 3 electrons. If oxygen is going to gain electron, it can gain 2 electrons. So therefore, this is a perfect donor and a perfect receiver. Just that they don't have just exactly this. This one has more than this guy needs. This guy needs 2, but this has 3. So therefore, they need to pair more than one atom with each other before they can have a balanced structure or a balanced compound. So to know that, the way you do it is that to know the number of aluminum that is needed, just look at the number of electron that is needed in the case of oxygen. So therefore, you will need 2 atoms of aluminum. If you want to know the number of atoms needed for oxygen, then you look at that of aluminum. How many electrons does it have to give out? So that means that you need 3 atoms of oxygen as well. So the 2 of them will bond together like that, and they will bond such that Al is Al3 plus because it's losing 3 electrons, and oxygen is O2 minus because it's gaining 2 electrons. So 3 of these guys would gain. So if 2 of these guys is giving out 3 electrons each, that means that total electron that is given out by these is 6 electrons given out. Each of these will receive 2 electrons each, and 2 in 3 places. That means that they have gained what? They have gained 6 electrons in total. That's the way it works. So let's do one more now. Let's do one more. So we have been able to pick somebody from group 1, and then we've been able to pick somebody from group 3 and group 6. Yeah. So let's pick somebody from group 1 and somebody else from group what now? Yeah, let's pick from group 1 and group 6. So let's use sodium because of time. Let's use sodium and oxygen. I don't need to write that configuration again. We know that sodium, if you want to become anything, it can lose 1 electron, and then oxygen need 2 electrons. So what do? You switch their places. So therefore, how many sodium will you need? 2 of it. So you have Na2. And how many oxygen will you need? Just 1 of it. So you have Na2O. Now, this is an ionic compound of sodium and oxygen. So what is the implication of this? You have 2 atoms of Na plus, or 2 ions of Na plus, and you have what? 1 O minus, O2 minus, 1 O2 minus. Please take note of this sequence. So now let me give you random thing now. So if you have K plus and you have, let's say, looking for an electronegative element. If you have K plus, let me use, you have Na plus and you have O2 minus, like we have done now. So all you have to do is to switch the place of their power. So this will be Na2 and then you have O here. I want to look for more ionic compounds to form. Let's say you have Mg. Let's say we have Mg2 plus, and then we have Cl minus. So in this case, what will happen is that Cl is having just 1 and Mg is having 2. So therefore, they will switch place. Mg will take 1 and Cl will take 2. So we have MgCl2. That's exactly how we know the way the compounds always form. So we know that, oh, this one has 1 atom and this one has 2 atoms. So all of these are compounds. All of these are compounds, and they are ionic compounds. So that's basically what happens with the formation. Now, there are this guy called transition metals. Transition metals, what happens to them is that they have what we call variable oxidation states. They have variable oxidation states, and this is because you remember when I taught you about the electronic configuration of transition metals. Notice that there is always a D and there is always the S orbital. There's always a D and there's always the S orbital. For instance, if we write for scandium, if you write for scandium now, so let's start. That would be 1s2, 2s2, 2p6. We have 3s2, 3p6. Then we have 4s2. Then we have, I think what follows here is 3d1. Now, for this scandium now, we know that it belongs to group 13, and you can see that it has 4s2 and 3d1. The highest energy level here is actually 4s2, is actually level 4, but you can see that the 3d is actually way higher in terms of as we are increasing in energy level, the orbital. So the 3d is actually higher than the 4s in this place. So that is why for transition metals, their outermost shell or their outermost electron is not restricted to only this number 4, energy level 4, which is the higher energy level. The 3d is also, the 3d subshell is also, it can be energetic enough, and it can also participate in bonding as well. So therefore, for transition metals, transition elements, they bond not only with this 4s guy, they also bond with their 3d guys as well. And this is what is responsible for their variable oxidation states. So at the point they lose electron, and sometimes they share electron. So they can lose electron and they can what? They can share electron. That is why for most transition metals, they have what we call the ionic property, and they also have what we call the covalent property. Since I'm not discussing covalent property in this video, I'm not going to be talking too much about them. So for transition metals, like I've already told you, they are outermost, and this is why when we want to determine their the group that they belong to in the periodic table, or the total number of electrons in their valence, we always use the S and the immediate D, the S and the immediate D that follows them. So we have explained this one in previous class. So in case you don't understand how what the little I just said about transition metals now is because you have not seen the previous class, and you need to go and see the previous class to get a proper understanding of what I'm talking about. So that is just the summary of part 1. But there's one guy I wanted to let you know about, is this guy, hydrogen. So if sodium is in the +1 state, and that means that it belongs to group 1. In the periodic table, hydrogen also belongs to group 1. By the way, I told you when I was teaching you periodic table that the only reason why we are putting it there is because it has 1 electron in its valence shell. But given every other property that those group 1 guys have, hydrogen should not be there. So hydrogen does not really necessarily have a group in the periodic table. It's just a floater floating around everywhere. So I'm going to ask you a question. For sodium and chlorine, I've already established that they are perfect match and they form this compound, NaCl. But in the case of hydrogen and chlorine, the electronic configuration of hydrogen is 1s1. For these, it was 1s2, 2s2, 2p6, 3s2, and I think 3p5. For chlorine, yeah, I wrote that somewhere there already. So, looking at the electronic configuration of this guy, you notice that this guy has 1 electron in its outermost shell, and this guy has 7 electrons in its outermost shell. They look like perfect donor and perfect receiver. So therefore, this one can actually lose 1 electron to this. But the question is that if hydrogen is going to lose its electron, what will he have left? If he wants to attain stability, like I said, you can either attain octet structure or duplet structure. So hydrogen is a perfect donor by virtue of the fact that it gains 7 or it loses 1. So therefore, it will favor the lesser guy. So if he wants to lose 1 now, if you lose the 1 electron, the question is that, will you now form a duplet structure or will you form the octet structure? Unfortunately, in the case of hydrogen, it probably does not have electron again, and that is even a lot more chaos than we expect. So therefore, hydrogen would rather not lose its electron. Instead, it is going to share its electron instead. That is why potassium chloride because potassium, sodium, and hydrogen, they are all in the same group. Potassium chloride, sodium chloride, they are ionic compounds. But HCl is not an ionic compound because hydrogen is not losing its electron in that place. In our next class, I'm going to be explaining about this better, talking about covalent compounds and covalent bonding rather, and dative bond as well. So that's it for today. Don't forget to like, comment, and subscribe to the channel if you have not. I'll see you in the next one.